I sure like this lab. This is where I, as an undergraduate here many years ago, I got to take the ECE 147 series, which is the controls lab, which takes place in this room, not surprisingly. And then later as a graduate student, I got to teach it, or TA it, serve as a teaching assistant for it. And that's fun too. You get to see, oh, the poor students are struggling, you know, and you're like, ah, yes, I remember what that was like. So I have a lot of this lab will always have a special place in my heart, and I'm excited to share some of its neat features with you. So I'm a fifth-year graduate student in electrical and computer engineering, and I work in controls. And what controls is, in case you haven't heard about it, or control theory or control engineering, is it's a sub-discipline within engineering that uses math, not surprisingly, to make models of physical systems that you want to control. And it uses math to design algorithms called controllers that will make those physical systems behave how you want. So that's kind of abstract, so let me give you an example. An example is a cruise controller in a car. So here is a cruise controller in a car. I mean, just don't even look at the screen for a second. Just you want to go 70 miles an hour. You plug that into the cruise controller. The cruise controller pushes on the gas. You know, it reads the sensors on the wheels. You can tell that you're only going 60 miles an hour. There's a 10-mile-an-hour difference, and so it can push on the gas to make the 60 miles an hour go up to the 70 miles an hour. So how does it do it? If you are a controls engineer, you will learn various tricks of the trade. There's a lot of tools with just pen and paper that you can do that you'll learn in the ECE 147 series. And then there's also computational tools that you can use that cost thousands of dollars, and you can use them for free and get great deals on them here at UCSB. So let me just tell you a little bit how a controls engineer, suppose you work at a car company, and your boss comes to you and says, I want you to make a cruise controller for this new car that we're making. So one way that you might do it is you might go to your favorite controls tool, MATLAB. So maybe, has anyone heard of MATLAB? Yeah, okay, some people. So it's sort of like, I mean, it's a programming language. You can do all sorts of different things with it. It has a lot of bells and whistles. It's kind of expensive. And one of the bells and whistles is, instead of writing a program as in like a text editor with a bunch of, you know, words and stuff, you can also write a program in a block diagram format like this. So each one of these things is essentially a function like you would write in a programming language. Here's a function, the cruise controller function. Here's the car function. And let me tell you about what this is going to do. This cruise controller is going to take two inputs, the desired speed and the actual speed. I've just set the desired speed to 70, like you would do if you were the driver. And the actual speed is going to be read from this car function. This is one of the actual speed is the output of this car function here. We'll get to that in a second. And this cruise controller from those two inputs is going to figure out how hard to push on the gas. Somewhere between 0 and 100%. So not pushing the gas at all, or 100%. It's flooring the gas. Let's see how it does it. Double click here. So this is just one of many possible controllers that you could do. This is kind of a simple one to wrap your head around. There are two inputs, the desired speed and the actual speed. I'll take the difference between the two. So you want to go 70, you're only going 60, so there's a 10-mile-an-hour difference. I'll multiply that by some number, maybe 5. You as a control engineer will have to figure out what's a suitable number. And that would make 50. 10-mile-an-hour error times 5 is 50. That's how hard you push on the gas, 50%. So a 10-mile-an-hour error, you push halfway down on the gas pedal. If there were a 20-mile-an-hour error, maybe you wanted to go 70, you were only going 50. Now there's a 20-mile-an-hour error, times 5 is 100. That means you would push all the way down. You would floor it if you had a 20-mile-an-hour difference. If there's a bigger error than that, this would actually be more than 100%. So you'd have to put some, in a real thing, you would have to push, you know, have some logic in here that would limit it to 100%. Fine, okay. So this is one control algorithm. Take the difference, multiply by some number called the gain, you decide, and that's how hard you push on the gas. That's that block. That goes into this car block. Let's talk about the car block. So from the standpoint of a cruise controller, all a car is a function that takes a sequence of gas values, how hard are you pushing on the gas, and there's some sort of speed that comes out. That sequence of gas pedal pushes results in some sort of speed. You know, it goes through the engine, the tires, the road, and so on. But from the standpoint of a cruise controller, it's just essentially a function. Gas goes in, speed comes out. Let's see, how does it do it? Well, I'll tell you, it's going to use Newton's second law. You guys have taken physics, presumably. Remember Newton's second law? Okay, it turns out that physics still applies in college. So, and so it's F equals ma, right? The sum of the forces equals the mass times the acceleration. So just for simplicity, the gas here is essentially the force that you're applying, because it goes through the engine makes a torque on the wheels that turns into a linear acceleration. So this is essentially the force. There's some sort of mass, so I just made it 1 for now, for simplicity. F over m, that's the acceleration, right? So that's the acceleration. If you integrate the acceleration, you'll get the velocity. Why is the integral symbol represented as 1 over s? You will learn. You'll take a signals and systems class that has to do with this thing called the Laplace transform. This is not important. All you need to remember is that you already know. You integrate the acceleration, you get the velocity. And that's the actual speed. That's the speed of the car. So there's a very simple model for a car that uses F equals ma, Newton's second law. And that is just that would be a nice, decent first cut of an algorithm that would take the gas and tell you what should the speed be. Okay, so armed with these two things, you can essentially run the program. It's essentially will numerically simulate what's going on, the speed of the car and so on, and I will show you the results. So this is the gas that you're applying. This is the speed of the car. I will just read this to you because you can't read the tiny things. You start at 60 miles an hour and you go up to 70 miles an hour, and you stay at 70 miles an hour. It's very nice. It's doing what you wanted. You're actually reaching your desired speed in about 1 second. It's actually pretty aggressive. It's like, you know, and then suddenly you're at your desired speed. The gas goes from 50%, so you're pushing down 50%, and then that slowly goes down to 0. So the cruise controller is slowly letting off the gas as you reach your desired speed. Question for you. There is an aspect of this prediction, of this performance, that does not reflect your intuition for how a car works. These curves are not exactly physical. Why not? Does anybody see something? Say again, please? Yes, there's essentially no acceleration after you get up. There's no gas being applied here. Yes, exactly right. Said another way, you can't go 70 if you're not pushing on the pedal. As soon as you let go of the pedal, the car's going to slow down. Why is this model deficient? What did I leave out? Please. Friction. Friction, air resistance, all these things that would slow down the car, that would make it so you still have to push down on the pedal. If you remember the F equals ma, there was no term for friction or air resistance or whatever. It was just you apply this force, the velocity is going to keep going like that. So that was the deficiency of this model that I did on purpose, but you as a controls engineer will learn what sort of ways that you can get away with, what sort of deficiencies are acceptable. Okay, so there's a model. It's not too bad, it's not too great, but it's fine for pedagogical purposes. Now, I should point out, nothing involved any of the hardware. All of you could go home, you could buy the student version of MATLAB, you could plunk away on your laptops, you could do this thing and experiment all day long with MATLAB and Simulink and so on. Have a great time. You don't need any hardware for that. Let's talk about the hardware because that's why you're paying all this money to go to college, is so you can play with fun hardware, right? Okay, so let's talk about that. So when you take the ECE 147 series, you will get this hardware. You'll get some teammates, you'll get this cart. The cart has a little motor on the bottom that has this little gear. This is a gear also, so it can move back and forth like this. There's also a little encoder here, a rotary encoder that can measure the angle of this gear. This gear is not actually driven at all. There's no motor attached to it. All it does is just read out what is the angle of the gear. And you can figure out using the sensor, therefore, what is the position of the cart along the track. Does that make sense? So you have one actuator, the motor, one sensor, the rotary encoder, and from there you can design a controller very much like the cruise controller that we were seeing. That's if you want it to be at 1 foot over, the 1 foot position, and you're only at the 2-inch position, you can take the difference between those two, apply some voltage, that voltage will drive the cart over. So you can use the same math from the cruise controller to the cart. And that's what I love about controls. You can use essentially the same math applies to all sorts of different physical systems, to simulations of cruise controllers, to carts, or pendulums, or rockets, or temperature controllers, or chemical processes. It's all different physical systems, but the same math. Okay, so once you can drive the cart around, next challenge. Here's a new cart. It's attached via a spring. It has a sensor, but no motor. There's no motor that can drive this cart. This is purely a driven cart that is driven by the motion of this cart. Suppose now, so this is kind of like a 3D printer. You think of a 3D printer, there's a stage that has to move around. And everybody, you guys have seen 3D printers before? So there's a little stage and there's a nozzle with the hot spigot of plastic that shoots out plastic, right? And that stage is driven by some motor, and then there's a belt. There's some sort of rubber belt that can move the platform around. That's modeled by this spring here. If you crank the motor over, the platform is not going to perfectly move over instantly. It's probably going to wiggle a little bit. The spring serves the same purpose of modeling that wiggling behavior. So this is like the stage, this is like the motor for the 3D printer, and suppose you wanted to move the stage over by 1 foot as fast as possible. One thing you could do is move the cart over as fast as possible by 1 foot, and this thing will wiggle around crazily. the thing that I want to tell you is when you take the ECE 147 series, you will learn how to design a controller that doesn't just do the simplest thing of moving over one foot, but it will actually perfectly wiggle itself to compensate for the motion of this thing. So this driven cart here, the thing that you want to be really fast and still, will move instantly across, and then this thing will do all of the wiggling and take out all and compensate perfectly for the motion of the spring. You'll get that for free. It comes for free from control theory and the math. I think that's very cool. Once you've done this, it's now time to graduate to the actual pendulum. So not surprisingly, you crank on this thing here, and if you look on the top here, there's another little black sensor. This is another rotary encoder. This is 0 degrees, plus 90, minus 90, and the whole point is, can you design a controller now that doesn't pay attention, you can take all this spring off and everything, that just pays attention to the pendulum angle and tries to compensate perfectly. So if it starts tipping this way, the cart will move and catch it. Starts tipping this way, the cart will move and catch it. So you'll learn how to design a controller that will keep this thing perfectly balanced straight up. And I will now show that to you. But we've been doing this sort of competition, sort of like when people talk about control theory, they typically have pictures of like the Terminator, because it's like, you know, Skynet. You're designing algorithms that will run in robots, and the robots are going to become alive and come and kill us and everything. So just to sort of reassure you, we're going to have a little, in the spirit of Skynet, we're going to have a little competition. Humans versus the machine. So I'm going to demonstrate the balancing on this smaller machine. This is just like the other one, except it's a rotary pendulum. It goes around in a circle. It rotates instead of moving on a track linearly. And it's going to try to balance the pendulum. Before we do that, I would like 2 volunteers. 2 volunteers to come up, and what you're going to do is you're going to balance these pendulums. We have sort of a running board on the side here. If you balance the pendulums for 10 seconds, you can put your name up. Then in the fall, you can come back and tell your friends, oh yes, this is me, I balanced the pendulum, and so on. It's very cool. There's a lot of prestige here, no pressure. But I need 2 volunteers to come up, and we'll balance the pendulum. Please. And one other balancer, please. So, you volunteered first. Which one do you want? Big one? What's your name? Abel. Please come, yeah. And Jacob. Sarah, what was your name again?
Abel, like Abel.
Abel, okay, Abel. So Abel and Jacob are brave volunteers. We're going to have a practice round first, so you can just sort of get a feel for it. Go ahead and try to balance it and see how it feels. It's actually kind of hard. I will say that Jacob got the short end of the stick, ha ha ha, if you will, because if you do the math, the thing that causes the pendulum to tip over fast is called the moment of inertia. Maybe you remember from physics. And the moment of inertia of a rod is 1/12 ml squared or whatever. What it boils down to is that because this rod is shorter, it has a smaller m, a smaller L, and it's about half as big in both dimensions. Anyway, it's about 8 times harder for you. Sorry about that. That's how it goes. All right. So once you just, do you have a feel for it? You ready for you're ready. You were born ready. Okay. What you all are going to do, you don't get off the hook either, is you're going to count down from 10, like New Year's Eve. 10, 9, 8, and so on. And also, while you're doing that, I hope it's hard. I know it's hard, but try to multitask. I want you to pay attention to how much the tips are wiggling around, because it's hard to balance these things. And one metric that you use as a control theorist is to figure out how good is your controller is how still does it make it? How close to the desired point is my controller actually keeping it? So the tip, yes, exactly. So you can see the tip's not moving very much. That means it's a pretty good controller. Good job. Okay, ready? So I'll say 3, 2, 1, go, and then we'll start. 3, 2, 1, go. 10, 9, 8, 7, 6. It's okay. All right, it's okay. It was a practice round. You want to do one more? Yeah. Okay, and keep going. Definitely keep going. We'll go for the whole thing. Okay, ready? I like that. I haven't seen that before. Okay. 3, 2, 1, go. 10, 9, 8, 7, 6. Oh, cross coupling. All right. one more, and then we'll call it a day. Okay, ready? 3, 2, 1, go. 10, 9, 8, 7, 6, 5. That's okay. 4, 3, 2. Come on, people. 1. All right, nice job. All right, so Abel, write your name on the Hall of Infamy, and Jacob, thank you for playing. Yes. I will say, thank you very much. It's very brave of you. I will say that no human has been able to balance the 1-foot pendulum for 10 seconds, period. Many have come and failed. It's really hard. I mean, I'm a controls engineer, and even I can't do this. So, this is pretty much my whole PhD has been like me trying to balance this thing. It's very difficult. Okay, so let's see how the robot does. So at the end of the ECE 147 series, you will have made a block diagram that looks like this big complicated thing. So way over here on the right, there's this pendulum block. And under the hood here, it has one input, which is the motor voltage. Essentially, you're driving this motor here that's moving the arm back and forth. There are two outputs. What is the angle of the arm? This arm here, so this is 0, 45, minus 45 degrees. There's also this little encoder here that's the angle of the pendulum, 0, plus 90, minus 90, and so on. So there's two sensors and one actuator, the motor. That goes into this big old thing here, and this whole thing here is essentially the controller. So there's a controller, and it's going to do two things. There's two sub-controllers under the hood. One of them just it pumps energy into the pendulum. This guy's actually going to swing up the pendulum. The swing-up controller is actually a lot harder. Well, it's a very different problem than a balancing pendulum. Once it gets up to the top, then this other balancing controller kicks in, and it just pays attention to the angle of the pendulum and makes very minor corrections. So those are very different problems, so there's two different controllers for doing it, and this one will switch back and forth between them. Okay, so let's see it do it. We'll connect to the hardware. Okay, and here we go. Skynet. Oh no, okay, so the robot is going into what's called a limit cycle. I'm going to help it here. Come on, buddy. I know, I believe in you. Okay, there we go. It's been a long day. Okay, so once it kicks up, you can see it's doing very well. You can actually even bother it a little bit. And you can see that the robot will immediately, okay, and then it gets into this limit cycle. He's embarrassed, he's got stage, what is it called, performance anxiety. So you can bother it a little bit. It'll, it might tip over, but the point is this encoder here has 4,000 ticks, 4,000 measurements per revolution. It means that it can actually, if you perturb this thing even less than the distance, the thickness of a human hair, the robot will know. The robot can handle it. So this is great because these things are way more precise than you as a human can accommodate. And you can leverage them with your knowledge of control theory. You can leverage these very powerful sensors and actuators that we have. So I invite you, not at this point, but I'm going to wrap up in just a second, and I invite you to come up after this and hit the robot to go home and tell your friends that you bothered a robot. You live to tell the tale. Okay, so anyway, so this is the controller. This is essentially the output of the ECU 147 series. And I want to just show you one more thing just because it's so fun. So I'm going to run pretty much the same kind of controller, but this controller is a little bit different. What I've done is inside the upright controller here, I've programmed in some set points. What it's going to try to do is it's going to try to balance the pendulum. That's given. But it's going to try to do it at different points with the arm balanced at different points. So imagine, like I told Jacob, I want you to balance the pendulum here, and then 1 second from now, I want you to be over here balancing the pendulum as fast as possible. So you'd have to sort of whoa, go over here and then go over here. It would be very hard, right? In addition to balancing the pendulum, you've got to do this funny dance. Very hard for a human, very easy for a computer. Let's see. Again, it will swing it up again. It's kind of fun watching it swing up, especially when it works. Ah, poor little guy. I know you're sad. Okay. So what it's doing, you saw that jolt. It'll jolt again in a second. What it's doing is it's trying to balance the pendulum over here, and then kind of really quickly get over here and balance the pendulum, and just kind of go back and forth. Balance it here, balance it here, balance it here. And if the controller, this is not a great controller, if the controller was tuned really well, it would go so fast. It would just go zoom and tip the pendulum over, zoom over here, pick it up, and then tip it over that way, zoom over here and pick it up. A really well-balanced, well-tuned controller is a beautiful thing. Now I want to point out one little thing though about this. This is the last thing I'll say, and then you can come hit the pendulum. You can see that every time it jolts a little bit, the whole table kind of moves a little bit. And you can see that when designing the controller, so when you design a controller, you make certain assumptions, like the thing about friction, right? There's no friction in our little, in our car or whatever. You made the assumption when we designed the controller that this thing is totally stationary. It's fixed, it's set, it's never going to move. But this thing is clamped to the stand, and the stand is clamped to the table, and the table has these long legs that can vibrate around. So let me show you what happens if you start violating the assumption that this thing is perfectly fixed. What I'm going to do is I'm going to remove these stands here, remove these clamps, and so there will suddenly be a little bit more vibrational wiggle room, so to speak, literally wiggle room, and we'll see what happens. So taking off the clamp, let's see what happens. See, it wiggles a little bit more. Whoa. Okay. And I happen to know that if you move the stand, because I did this while I was setting up for this demo, if you move the stand over a little bit to a particular spot on the table, that turns out to be that turns out to be very disadvantageous for the poor robot. Okay, shush. Okay, you got to really develop a, so I'm gonna now let go, and you'll see what happens if it tries to balance it over here. See? How crazy is this? So I don't know if you've heard of the Tacoma Narrows Bridge, but it was a suspension bridge. The engineers did not account for the way that the wind would make the bridge vibrate. There was a vibrational mode that they hadn't accounted for, and the bridge essentially vibrated itself to pieces. The same thing is happening here. There is an unaccounted for vibrational mode, which is the stand and the frame are rattling on the table here, that the engineer did not take into account when designing the controller, and it wreaks havoc on the controller. You, as a controls engineer, will learn to sort of probe around in a system and try to figure out what vibrational modes or other modes you can safely ignore and which ones you have to account for. So we can account for this one by just clamping it down harder, but I just wanted to point this out to you as kind of an interesting real-world thing. And I'll let the robot move back into its little safe position over here. I know, it's been a long day. So I'm happy to answer any questions. I'm going to clamp this thing back down so the poor robot doesn't hurt himself, and I invite you to come up and hit the robot. So thank you for paying attention to me. Yeah. Any questions while I clamp this puppy back down? Yes, please.
What if you change the material?
The material, like the material of the rod, for example. Yeah, that will change, like the ML squared thing. That will change the moment of inertia, how fast the rod can tip over. So if you made it out of tungsten or something very hard and or something very dense, it would not fall over quite as easily instead of just aluminum. And it would essentially just be some new term that you would plug, or some changing, it would be a different term that you would have in your equations of motion for when you're designing the controller.
Would it be harder if it was rubber? More elastic?
Yes, and this ties into the whole vibrational mode thing. If this thing is suddenly non-rigid, there's a whole bunch of equations of sort of beam flexure equations called the Euler-Lagrange beam flex equations or something that have to do with how a beam vibrates. We can make the assumption, because this is metal, that this is going to be hard and not vibrate. But if it was rubber, it would be a big pain in the neck. Yeah. Anyone else? Okay, well, I know you're all excited to come up and hit the robot, so feel free to come do that. Or not, if you want to stay on the robot's good side. Yeah, cool. And I hope you have a good rest of your tour.
Thank you.
Thanks a lot. And when it gets into this mode, oh, it actually hit my laptop. Robots, machines fighting machines. Who will win? Actually, if I rotate this just a little bit more, you're probably wondering that's what the pens are for. It's for the pen, so it doesn't kill itself.